Okay, so hi everyone. My name is Imen. I'm a senior statistician in Oxford, and I work on big data mainly, and I teach stats in an MSc of Global Health Science. So my students this year are mainly medics, and I do also run trainings for medical staff and for computer engineers as well. So I teach different sorts of people actually. Okay, so this is the second session in stats in this research fellowship series. So you have been introduced to summary statistics, data distribution, and very quickly to parametric versus non-parametric tests with Chris. And I had a look at Luai's session as well, and I think he mentioned measures of association. So I think you probably have been introduced to a few things that I'm going to kind of go into more details in this session. So in my slides, there's a lot of R code. When we teach stats, we need to kind of be able to run those stats. So I know you may use, I don't know, you may be using SPSS or Stata. I think there's a lot of softwares out there that you can use for linear regression. So I have put R code in my slides just because it's open source, so doesn't require any license. So that's why I have made that choice. But what I teach in our MSc is based on Stata, for example. So you can ask me questions on Stata as well if you like. So there's a lot of stuff there in the slides. So I'm not going to go through all the details about the R code. I think it's good that it's there for you guys to kind of practice later if you want to run some stats on your data sets. So it's all there. And I made that choice actually to incorporate R codes in my slides. However, it doesn't, we won't have the time really to go into the R code in details, and as you know, it requires a little bit of practice in order to be able to use R, especially if you have not used R before. Okay, so I hope you like my background. So I'm not like a Zoom user. This is probably one of the first times I'm kind of running a presentation in Zoom. I use a different software for presentations. Anyways, but I like this background. So by the way, I'm Tunisian. So this is not Tunisia, but it's kind of very similar. So I hope you kind of like my background. So I have not really prepared polls this time. I think I'll try to do that for the next session, logistic regression. So for the time being, I'll probably be very happy to interact with you guys on the chat. So I'm probably going to ask you questions, and please feel free to submit your answers on the slide. Oh, thanks, Nizar. You like my background. That's great. Okay, guys, so let's start with linear regression. It's only, oh yeah, by the way, so this is 1 hour and a half session. We're going to have a break by 5:50 for you guys. I'm going to take 5 minutes question by 45. By 5:50, we're going to have a break for 10 minutes, and we are going to have a second part starting at 6 to 6:30. So it's 1 hour and a half session for this linear regression session. Okay. Yeah, so in this session, we are going to get a little bit familiar with the linear regression model. Simple ones, actually. We're going to look into the correlation. What do they mean? We're going to run linear regression models in R and interpret the output. And we are going to explain a little bit ANOVA tables and how to use them to compare group means. And then the last bit is about the assumption of a linear regression model. So I think I need to put this in the context of you guys reading papers. So if you read papers about blood pressure, for example, as an outcome, most of the time is going to be like a linear regression model in there, or a t-test, which is the basic form of a linear regression model. So I think what we want you is to be able to kind of interpret the results that you see in papers, in tables or in plots, and also to be able to run your linear regression model in your data sets, whether you use Excel or R or Stata. I think that's sort of being independent a little bit in analyzing the data is really very important. Whether you're a medic, statistician, whatever, I think you will probably need to have a first look at the data before anybody else is going to analyze them. Okay. Yeah, so in my slides and on my lecture, I have a friend, and you guys will have the same. She's called Jane. She's very, very smart, and she's going to appear in red boxes in my slides. And every time you see the red boxes, it means it's really, really important thing for you guys to remember. Okay. Yeah, so the content of this session, I'm going to talk a little bit about correlation, and then I'm going to introduce the simple linear regression model. In the third section, we're going to introduce ANOVA tables, and then we'll probably have a break and then carry on with the ANOVA and the regression diagnostics at the end. Okay, so let's start with the correlation. So when people say correlation, we don't really know what they mean. It's a very vague term used to mean probably association or relationships. So when I use the word correlation in this session, I mean linear correlation. So my main interest is to look at a continuous variable, continuous outcome like blood pressure, like a biomarker, CRP, whatever continuous outcome you're interested in. And I'm trying to see whether this outcome is correlated with another one. So for example, okay, so these are like the different types of correlation we can talk about: positive correlation, negative correlation, no correlation. So in this first panel, there is a positive correlation, which means like when the value of y increases, when the value of x increases, the value of y will increase as well. Like this could be like the case of, for example, SBP versus age. So you might probably know very well that actually the older you get, the higher probably your blood pressure is. It could be BMI, it could be many things. So this kind of positive correlation when the two variables vary together is called a positive correlation. Negative correlation, the opposite, when actually the value of x increase, the value of y is going to decrease. And you're going to have this kind of shape. No correlation at all when you actually don't see any pattern in your scatter plot. So this is, by the way, called a scatter plot. Okay, so I'm having an example here. So this is showing data on ice cream and swimming pool depth. So ice cream, the number of ice cream sold is on the x-axis and the number of swimming pool depth is in the y-axis. So this data is from the US, and I think there's 100 points here. So data were collected on each day of summer. And what actually they have collected are two numbers. The first number is how many ice creams have been sold and how many swimming pool deaths have occurred during that day. So you end up having like 100 points here. So I don't know what you think about this correlation. I mean, I'm putting like a hint here. It doesn't really seem plausible. And I want you guys to try and explain why are we seeing a relationship between the number of ice cream sold and the number of swimming pool deaths? Do you think we are more likely to die in a pool if we eat like a lot of ice cream? So I want you guys to kind of think what could be explaining this relationship between the two variables. I think we all agree it's not a genuine one. So I'm waiting to see your answers. Okay, so Luma is saying it's not plausible. That's summer, yes. Yeah, all the points have been collected in summer. So I don't know in which like city actually in the US, but anyways. You need a thorough explanation before you use correlation. Perfect. That would be my conclusion all day. Luma, summer is a confounder. So I think you need to think a little bit. I think you're in the right, yeah, I think you're right in the right direction. Season of both. Maybe just luck. Yeah, it could be just luck. I think there's a lot of correlation that actually just coincidental. It just doesn't make any sense. It's just there. Swimming during summer. They do swim and they do eat ice creams, but you need to think why they, like, there are like a lot of swimming pool death when actually there is a lot of ice cream sold. And I think you need to kind of think when actually both are going to be high numbers, when both are going to be low numbers. Okay, so number of people who came to beach increase. Yes, yes, I think the more people you have, probably more ice cream sold is going to be. Correlation doesn't mean causation, thanks. Yeah, that's a very good. Summary, swimming and eating ice cream both in holidays or when people are not busy. Yeah, so if that was the case, I mean, even if in summer, I didn't get my answer, so I'm probably waiting for the others to kind of provide me with the answer. I think number of people tend to swim when it's hot. Yeah, Ru'a, yes. Same goes for ice cream. Absolutely. Thanks, Ru'a. So I think, yeah, I think we have the answer. Yeah, absolutely. It's a thing with the temperature, really. So although it's summer, although it's like during 3 months of summer, but temperature could be very different. So in my country, Tunisia, we don't swim the whole summer. June is getting very cold these years, and August is very hot. So I think it's probably depend on the temperature factor. So here, what I try to do is to color the points according to the different temperature on those days. And you can see actually here on the top, you have like colors that actually tend to be more red than the bottom, sorry. Yeah, and that's because probably these are very hot days, so people tend to eat a lot of ice cream and to go to the swimming pool a lot. So that's why you see this kind of high numbers that are correlated with each other on the top. And the same goes for this purple numbers. Actually, I think only the brave people will go to swim when actually it's like between 10 and 20. And you can see like for this very blue points, actually, although people do eat ice cream, I do myself, even like in Oxford, it's never hot. But I think we do like appreciate ice cream, although we don't have the opportunity to swim. So I think it's thanks guys for your answers. So that was like my point, is actually you might end up having like a relationship that doesn't mean anything just because they both are related to a third factor that we call confounder in epidemiology, or actually it could be just by chance, it could be completely coincidental. So I think you have said that in the chat, correlation does not imply causation. Please remember that. And I think like a lot of people do make that mistake when they read papers. You can see like a lot of people talking about very odd correlations on Facebook, on social media. Doesn't mean anything. I think people need to think what else could explain that association. So by magic, using a software, I remove the effect of temperature here. So you can imagine I'm here looking at like points that have been collected on days with same temperature, say on days with 30 degrees, for example. If you make that distinction, which means you just like fix the temperature and collect the data only on those days which have same temperature, you won't see any association, just because we remove the effect of temperature here if we consider only points actually with the same temperature on that day, on these days. So I think, yeah, so this is done using a software. This is what we call in-stats adjustment for a confounder, which is like removing or controlling the effect of the confounder in order to reveal the true association, and there's no association here. Okay, so Jane is going to say a few important things. So what a correlation does not tell you is why two variables tend to vary together. And I think this is a very good point. And as I said, correlation could be just by chance, or it could be like due to a third factor. Okay, so now how to quantify correlation? I mean, I think you've heard like people saying there is a strong correlation, weak correlation, moderate correlation, and I think we can have like different measures to assess or like quantify correlations. The most famous one is probably like Pearson correlation coefficient. So Pearson goes from -1 to +1. Here I'm talking about continuous variables, guys. So X and Y are two continuous variables, and I'm going to use Pearson only when I have two continuous variables. This is one of my assumptions here before using my Pearson correlation coefficient. So similar to the plots that we have seen before, so like when there is no pattern at all, Pearson is going to say R is equal to 0, R equal to 0, there's no linear correlation at all. When you have like a perfect negative correlation, perfect, which actually like the points are like on a straight line, this is perfectly decreasing together. So R is going to equal to -1. And when you have like a perfect positive correlation, the R is going to be equal to 1. But actually, these are like really very hypothetical like situations. In real world, you probably be in this kind of numbers. So for the first one, actually, I cannot really distinguish a pattern here, like visually, but Pearson correlation coefficient is telling me there's like a weak correlation there. In the second plot, there is a strong negative correlation. I can see a pattern here. I can draw a line that actually goes through these points. And on the third plot, there is actually a strong positive correlation between the X and Y. Okay, so this is our code. As I said at the beginning, I'm not going to go through the details. It's here for you guys if you want to practice, if you want to use these concepts on your own data. And I think it's very useful. We learn stats, but we need to know how to use them. This is like the command in R in order to allow me to, after actually calling my data, I'm here drawing a correlation matrix, which actually is showing me the correlation between biomarkers in my data set. So I have just like selected randomly some biomarkers in my data set, and I'm trying to look at the correlation between these biomarkers. So for example, in the row that I highlighted in green here, if we look at APOE1 and HDLC, you can see that correlation coefficient is equal to 0.8. And I think, guys, you probably know even better than me that actually there's some kind of biology there that would probably let you expect to have a strong correlation between APOE1 and HDLC. As you can see, like weak correlation between cholesterol and HDLC, 0.11. And you will have 1 on the diagonal here, just because HDLC is perfectly correlated with HDLC. So these are nice correlation tables. If you publish a paper and you have like nice variables in your data set, you can like put this correlation matrix in your paper. It's also a way for us to also know what are the variables that are correlated together. If you are doing like a regression analysis, for example, you cannot really put all the variables that you have in your data set. You need to look at your variables first and see what are the variables that are highly correlated, and then select those that are more or less independent. So, okay, so now it's a question for you guys. So I have 4 panels here, and I want you to rank them from the strongest linear association to the weakest linear association. And after that, we are going to look at the R correlation coefficient for these plots. So I want you to say, what's the panel that is showing the strongest correlation coefficient amongst the 4, and so on until the weakest correlation coefficient. So you can say it's A, B, C, D, or it's A, D, C, B, whatever you think is the right ranking from the strongest to the weakest. Okay, so you guys have different opinion on this. I think it's fine. I really like when actually people do not agree with each other. So we have like 2, I think, probably different opinion here. Some people are saying the C then the A, some other the C then the B. What about the rest? We want to see your, we have 37 participants. I'm waiting for more. Okay, thanks guys. So let's describe those associations. So as you can see in A, there's actually some sort of linear association here. We can see that the variable y increases with increasing value of x. I'm just going to look at the chart. Must the correlation start from a 0-point linear shape? Must the correlation start from a 0-point linear shape? Ru'a, if you can just like reformulate your question, just because I don't. So what do you mean by start from a 0-point linear shape? Yeah, so here we are ranking them from the strongest to the weakest. So this one looks linear. Okay, in the B, it's a curve, basically. It's not linear at all. So from what we said and what Jane has said as well, actually we use Pearson correlation coefficient only for linear association. So I won't naturally use the Pearson for the B just because it's a curve. It's a nice association. There is absolutely an association to investigate there. However, it's not linear, so it's outside the topic of our today's session. C, so C shows a perfect linear association here at the beginning, but then there's some sort of outlier. This is what we call an outlier. So that's like a point that is like far a little bit from the rest. In the D, there's no association at all here, just because, I mean, X is fixed, it's the same, it's one number, and Y vary. And there is an outlier here. So now I'm going to show you, I don't know if we have any other, yeah, no. Okay, so now I'm going to show you the Pearson correlation coefficient. Oh, sorry. It's perfectly the same. R is 0.816. So our Pearson correlation coefficient is not able to distinguish between the strongest versus the weakest, because in these plots, there's some sort of reasons why you end up having the same correlation coefficient. So let's start with the first. So we were expecting anyway the association to be linear, and we end up having a 0.8, which is something you would expect. On the C, there's a perfect linear association. It could have been 1 just because it's perfect. And just because of this point, actually, so I mean, if you have to draw a line between this point, the line would be between this outlier and the rest of the points. And I think like the effect of that outlier is to make the association look weaker, actually. So it could have been 1 and now it's 0.8 just because of that outlier. Here, there's no correlation at all if you look at the first set of variables, of points, sorry, and there is an outlier here. So just one outlier was able to create an apparent linear relationship that actually doesn't exist. So what I want to say from here is you need absolutely to be careful when to use our correlation coefficient, just because I think the stats need to be used like really based on some sort of assumptions, and the assumption here, you need to have a linear association first, and then R is going to help you to quantify how strong or how weak that association is. Okay, so first look at the plots. So Jane's ideas. Pearson correlation coefficient is a useful summary. Yeah. So it can provide a good insight for further investigation, and it can only be used when the relationship between the two variables is linear. Absolutely. First, look at the plot and then choose your summary statistic. It's very sensitive to clustering and outliers. Absolutely. Just because of these 2 points, we had a strong our Pearson correlation coefficient, and actually there is no association. Okay, you should, Auday, you should do data cleaning before the analysis. Absolutely, absolutely. So, I mean, unfortunately, like I'm jumping into linear regression here just because I think it's important concept. However, there's so many steps that you need to do before, when actually you're absolutely right, or you absolutely need to look at the data first, clean the data first. I mean, cleaning the data is kind of a lot of work, actually, because we don't want to manipulate the data. We don't want to change the numbers. We just want them to be as meaningful as possible. And that's a lot of work in itself. Okay, so let's now go to more serious things. Simple linear regression. So here, my aim is to try to explain, okay, I have a sample of participants with different SBP values, systolic blood pressure value. And my question is, why do these people have different SBP value? Why do they don't have like the same value? And one of the things that I can think of, I'm working with observational data, I'm working in cardiovascular diseases like department. So for us, age and sex are very important in order to explain differences between people. So one of my hypotheses is to say, these people have different SBP value just because they have different ages. These people have different mean SBP value just because they have different gender, they're either males or females. So I think I'm trying to see what kind of association I can kind of reveal between SBP and other things that could explain SBP. Okay, so some terminology here. So, I mean, I think there's in textbooks, people use different wording. So for my outcome, for the variable I'm interested in, I'm going to call it dependent variable. So this variable, SPP, depends on other things. It's also called a response variable. My X variable is, for example, age or sex, which is called the independent variable. It doesn't depend on anything, it's fixed. And I'm trying to see what's the association between these independent variable and my outcome, which is SPP. Okay, so some kind of, I think, a refresher. So this is a line, and I think you're probably familiar with these equation of a line. So I think we need two things in order to define a line. So the first one is the intercept, when actually the line crosses the y-axis, and then the slope, how steep the line is. Okay, so this is very basic, but it is actually one of the fundamental things in linear regression. So we are trying to kind of summarize the association between SPP and age using a line. Other than having like a big dot of points in your scatter plot, you want to have something that is simplified, a simplified version of the reality using a line. So that's why we need to remember what's the equation of a line. So now, in order to run my linear regression model between SPP and age, for example, I need two things: intercept and slope. Okay, I'm going to look if I have any questions. No. Okay, so this is some stats, math. I mean, it looks not very nice, I know, but this is how we call our intercept and slope. So I'm calling them betas. You can call them A and B. You can call them C and D, whatever. These are only letters. So for me, beta 0 is the intercept and beta 1 is the slope. I'm putting a hat here in order to say this is an estimated value, which means I'm going to use my sample in order to estimate the value in the population. I don't have the whole people. I have only a sample, which is a subset. So I need to really to make that distinction between what I'm doing, which is like called inference in statistics, which is like having some sort of conclusion out of a sample. And I'm trying to have an interpretation of what's going on in the population using my sample. So this is not the ones in the population. This is only an estimate from our sample. Okay. So I'm here going to show you a very famous example in linear regression. In most of the textbook, you see like these examples about like the height of fathers and the height of their sons, or the height of mothers and the height of their daughters. So this is one of the very first application of linear regression. So in this plot, I'm showing the association between daughter's height and mother's height. So as you may expect, you might, like the daughter's height will be, so the daughters will tend to be taller if the mom is tall, and it will tend to be like, I mean, short if the mother is short. But you might also expect that daughters whose mother is average height to have an average height as well. So I think this is kind of really natural deduction. And it's very sensible here to describe the association using a line. So if we were to assume this linear relationship, I think we need to kind of understand how to get to that line using the software in order to get the slope and in order to get the intercept. Okay, so I'm going to do some sort of estimation using the line. Okay, so as I said, my assumption is a daughter whose mother is average height is going to be average height. So if my mother is average height, I'm going to be average height. If my mother is tall, I'm going to be tall. Okay, it's not good. Anyways, so this is the point of the averages, or the point of mean. So that point belongs to the line. This is the first thing that I'm learning today. Okay, so now how can I use the line in order to make an estimation of a daughter's height? I'm going to look at her mother's height. For example, here, a mother's height is 58. If you're not very familiar with inches, I'm not myself as well, but I teach with that. Anyways, say, I don't know, like 1.65 m. Have no idea. But anyways, let's assume this mother has this height. So and we want to make some kind of estimation or a guess of her daughter's height. So we're going to use the line, and the way we use the line, we just like follow that line and then look into the y-axis in order to see what's the average daughter's height, and it's 61.3. Okay, so this is how we use the line. So I'm not going to really make any kind of estimation outside the range of the values that I have. For example, I'm not really going to be making any estimation in this area just because it's outside the average points that I have, the range of the points that I have. So my estimation is probably not going to be very good. I'm not going also to make any estimation here on the high values, just because I don't have any in my sample. So it doesn't really make sense to predict things in the population if in my sample there's no points like that. So I'm going to stick with like the range of the values that I have here. Okay, something really, really, really important in linear regression is what we call residuals. I mean, like the whole thing is based on that. So residuals are actually the errors that I'm making when I'm making my guessing, actually. So if I'm guessing, for example, say for this daughter here on the x-axis, so this is her true height. Okay. Sorry, this is a mother, sorry. So this is a mother, and actually this is her daughter. So her daughter is 60, and the mother is about 62. Okay, now if I were to use the line in order to guess what's the daughter height, I'm going to read the daughter height on the line here, and it's going to be 64 something. So what does that mean? It means that I'm actually overestimating the daughter's height using the line. Okay, so if I'm looking at the E3, for example, so this is a point that belongs to my data set. So if I look in the x-axis, this is the mother's height by the 68 something, and this is the daughter's height by the 70. If I were to use the line in order to make my estimation of the daughter's height, I'm going to read on the line here, and actually I'm going to read Y3 hat instead of Y3, which means that I'm underestimating the true daughter's height, which is fine. I'm always going to make some errors, and the idea is to minimize those errors. So those errors are called residuals. I mean, the errors, like the differences between the observation and the estimated values. Yeah, so what I was saying, that I will probably make errors anyway. So I'm kind of trying to summarize the reality. So it's okay to make errors. And the idea is to minimize those errors. And the idea behind linear regression, the linear regression line, is actually to kind of minimize those errors that are called residuals. Okay, so as I said before, I'm making like bad estimation sometimes, I'm underestimating sometimes, overestimating sometimes. So the idea is what the software is going to do is going to sum all those errors and try to minimize them, because you can draw different lines. So what's the perfect line really, according to the linear regression fundamental idea of minimizing the residuals, is to go through the points, or actually it's to kind of have the smallest differences between the points here, the estimated value and the true value. So by the way, the estimated value on the line is also called fitted value. So I think you're going to see this on my slides. Fitted value or estimated value is the value that I'm going to read on the line, and as compared to observed value. Observed value is what I observe in my data set. Okay, anyways, what the software is going to do is going to minimize those errors, but it's going to square them. And I think you probably heard, if you had any stat lectures at all, you probably have all the squares, sum of squares. And the idea behind squaring the differences is actually, if you sum them, if you add them, if you add this minus to this plus, they can cancel each other out, which means that you can have like +2, -2. If you sum them, you have 0. So you lose information about variability around the line. In order to not lose that information, if you square all these differences, you only have positive numbers. So if you sum them, you always get some sort of information about how distributed these residuals are. Okay, so the idea is to square those residuals and try to minimize those residuals. So hopefully you will never have to do that, but I think it's important to understand this idea about the residuals in order to understand the assumptions later. Okay, so let's start with one first example. So here I'm looking at the data set that has SBP and H, and I'm going to look at the R code for that, and I'm going to try and interpret the regression output. Okay, so this is showing SBP, systolic blood pressure versus age. I mean, it's really hard to tell whether it's linear or not, so I'm going to assume that. But I can test that and check that. This is one of the assumptions that I can test. For the moment, I'm just going to assume it's linear. I'm going to draw a line. In order to draw a line in R, I'm going to use the LM for linear model command. And as I said before, I'm not going through the details about the coding. It's only there for you guys in order to practice how to get regression outputs from R, which is open source. Okay, so I have a lot of numbers here. So if you remember, we need two things in order to define our lines. We need an intercept and we need a slope. And this is what R is going to give you. So I'm going to through the main things point by point. Okay, so say this is my main output from R or from Stata or SPSS. So I'm going to have these four columns that are very important. So the first column is the estimate of the slope and the intercept. So the intercept is called intercept, and the slope is the thing associated with the variable that you are looking at on the x-axis. So this is the slope. It has ages as a heading, and this is the intercept. Okay, so we're going to see how to interpret these numbers later. So this is the standard error, and I think you probably heard about this either in the previous session, or if you have seen confidence intervals with I as well, I think you may probably came across this. So standard error is actually, as I said, I'm trying to get this like simplified version of the reality, but I'm accepting that I'm making some sort of errors. Just because I have a sample, I don't have the whole population. And just because I have a sample, it could be like a small sample that kind of generates a lot of errors, but it could also be like a very heterogeneous sample. So say, for example, I'm collecting data on SBP, and I'm going to collect really different SBP values. I'm going to collect like some people have an average SBP values, and I'm going to collect like people with very different SBP values. This is a lot of heterogeneity there. So my standard error is going to be high. Standard error is actually the thing that is going to tell you how good is your estimation. So we want this to be very small. Okay, and it depends on my sample actually, so I don't have any kind of control over it. You need to kind of think about that when you set your study first. So this is a t-test. These are related to the t-test. So the t-test here is going to test whether the estimates are going to equal 0 or not. What does that mean? So if I have a slope that is equal to 0, it means that I have like a horizontal line like this. Okay, it means there's no association. I need to have the slope a little bit like this and not like that. Okay, so in linear regression, like horizontal line means no association. You have like a dot, a big dot of points, and you kind of draw a horizontal line. So the t-test is going to test whether my slope is equal to 0 or not. So how is that going to test that? The t-test value is basically a very simple idea. And it's really unfortunate you didn't get the chance to go into the details with Chris, because I think he had a lot of content in his lecture already. But anyways, so this the idea behind the t-test is actually, okay, so my idea is, how can I get the best estimate ever? We know that this is going to be reflected by the standard error. The bigger standard error, the bad my estimation is. So one measure is to try to divide the estimate by the standard error. Okay, I want the estimate to be big, and I want the standard error to be small. If I divide this estimate by the standard error, then I'm going to get numbers. If that number is big, it means like the estimate is like big enough as compared to the standard error that I can trust the value. In the opposite, if my standard error is very big and my estimate, it is what it is, if I divide it by a big number, I'm going to get a small value, and that's not good. So I want my estimate to be at least twice as big as my standard error, like to the 2 in normal distribution, 1.96, I think probably talks to some people. Anyway, so if you have this t-value above 2, that's a good thing. It means that my estimate is big enough as compared to standard error, so I can trust my estimate. So this is what the t-test is all about, testing whether the coefficient is equal to 0 or not. Okay. So now, how to interpret these numbers? I have my intercept, which is like the point where the line crosses the y-axis, and I have my slope, which is 1.05, say. Okay, so let's draw the line. This is my intercept, which is 74, and I have a slope about 1. So this intercept is actually correspond to h equal to 0. This is the value of SBP when h equal to 0. It's meaningless, doesn't have any sense. And that's because I'm not looking at all at these areas outside the range of my values, just because I don't have data there. So most of the time, intercept is meaningless. So what I'm interested in is the beta here, that is the slope. This is the thing that is relating SBP to h, and this is what I want to interpret. Okay, so what does that mean? Beta is equal 105 means it's actually for 1 year. If you are 1 year older in this population, you are, sorry, it's cold outside. If you are 1 year older in this population, you will get 1.05 higher SPP. Okay, so I'm going to say it again. For 1 unit increase in age, which is if you are 1 year older, you are going to have 1.05 millimeter of mercury higher SBP. This is how it goes. Okay, my beta relates age to SBP. So for 1 unit increase in age, I'm going to have 1.05 millimeter of mercury increase in blood pressure. Okay, and this is actually what you can see in the line. The more actually you're older, and the higher the SBP value is, and it increases by 1.05 for each year increase in age. This is the very basic interpretation for this. Okay, so now I'm going to show you a second example just before the break. This is about SBP and sex. So I wanted to have like 2 examples, one with the continuous exposure, which is age, and one with binary exposure, which is sex. It could be actually a treatment arm if this is in a trial, anything that is binary. Okay, so do people have different SBP value just because they have different gender? Is that the case? We are going to look at the box plots, and I think you've seen this with Chris yesterday. So these are 2 box plots. This is like the distribution of SBP values in males, and this is the distribution of SBP values in females. Can you really tell, I want you to kind of put that in the chat, can you really tell whether there's any significant difference between males and females according to their average SBP values? Do you see any differences, guys? The range of men is wider, that's true. There's more variability in the males. The line is at the same level almost. That's the thing. I mean, when you look at the scatter plot, sometimes you cannot really distinguish a line. And when you look at box plots, you're not able to compare them. So I think I kind of agree with all of you guys. Thanks for answering. Yeah, I mean, it's really hard to tell. And I think if I had to compare the medians, probably I would say males have a little bit higher SBP value. So I'm not going to guess. Hopefully there's linear regression there, and there are like software there in order to give me like some sort of idea about whether it is significant or not. So I need a kind of decision rule for that. Okay. Sorry. Yeah, so I mean, so this is a slide for software users. Every time you work with binary variables, categorical variables, whatever you want to call them, you need to tell your software, SPSS, Stata, or R, that these are level variables, which means that you need to look into the levels separately. Otherwise, the software is going to consider them as continuous, when actually 0 and 1 here in sex means males and females. It doesn't mean 0, 1 as a unit. So in all the software, there is always a way to kind of declare your variables are factor variables, indicator variables. In Stata, you add an I. In SAS, you put it in a class. Anyways, whatever the software you're using, you need to say something about the fact that these are like factor variables. So these are levels. So you're going to compare the mean SPP in those levels. You're not going to treat them as continuous. Okay, that's why I'm putting this here. Okay. So the way we do it in R, and actually just like using the factor function, and this is linear model with the sex.f, which is like the factor sex. Okay, so this is my output, and I'm going to look at how to interpret this. Okay, so this is the R output, and this is the line that is associated with sex. I think I'm going to skip that. Yeah. Okay, so I'm going to put those 2 numbers here in an equation. So my SBP is equal to the intercept plus the slope times sex, which is female here. So what does that mean? I think we need to interpret like these slope and intercept separately. Okay, so the 126 that I'm getting here is nothing else than the average in the reference group. So if you are working with binary variable, you have like 2 levels. For sex, you have males and females. So the software is going to choose what's the default. And I think most of the time it's the lowest category, the one which have 0 as code. and is going to compare the other level to that reference level. So in the output from the software, you're going to have like two numbers. The first one is the mean level in the reference group, which here is males. And the second number is going to be the difference between males and females. So this is how we read it. So this is, I mean, could be done really very easily, but actually just like tabulating the mean in males and females. You can see you have this first number that comes from the regression as well, which is the mean in the reference group. And you have the second number, which is the mean in the other group. If you subtract these two numbers, 126 minus 122, you're going to get the, here, the 3.98 millimeter of mercury. So this is the difference between males and females on average for their SBP values. And I think the problem is that it was like, I'm going to show you the box plot again. It was really, really hard to distinguish. You can see the scale here of SBP value. Those who said actually there could be a difference, actually they were like looking at the differences here. So there is a difference of about 4 millimeter of mercury between males and females. So it's hard really to tell from the plot. So that's why you need software to tell you that. Okay, so what I want you to remember is two things. You need a slope and you need to understand what the intercept means in this situation. Another way to do it is to use a t-test command, and actually you can really see that actually it gives you exactly the same result. So it gives you the means in the males and the means in the females, and the difference, the slope will be the difference between the two. So just like to summarize, linear regression when using one binary variable is nothing more than a t-test. It's absolutely exactly the same thing as a t-test. So you might ask me, why are we using then a regression instead of like a simple t-test? There are so many reasons for that. The first reason is that a regression model is going to give you numbers about like quantities. It's going to kind of quantify the association. Tests are going to tell you yes or no. You're going to reject the null or not reject the null. If you're using regression type methods, you're going to get numbers. These numbers are important in order to report in a paper to say, this is the mean difference between males and females in blood pressure. So that's why you use regression. You also have like a confidence intervals and p-value that goes with that as well. The second reason for using regression is also to be able to put more than one variable in the model. So I'm not doing this here. This is what we call adjustment. Like, for example, if you're looking at the association and you think you need to adjust for other factors like age and sex and, I don't know, BMI, smoking, etc. This is where the regression type of things is really, really very helpful. Okay, so let's take a break before we go to the ANOVA part. So I think I'm going to take some questions. Do you have any questions, guys, before we go into a break? The normality in stats, I think it has been overstated all the time as being like a key thing. However, it's not the truth. The truth is, normally distributed data is really very helpful. It is helpful, but it's not an assumption. It would be an assumption if you're dealing with small data sets. So it depends. If you have like a small data set, then probably assumptions about normality has like a lot of weight. And that's why people use non-parametric tests instead of parametric ones in small data sets. In big data sets, like the ones I'm dealing with here, or I mean, anything that is probably above 100 or 200, depends. I mean, it depends also how variable, how like heterogeneous your sample is. It's much less important. Like normality assumption is much less important. However, we still kind of look at distributions for so many different reasons. So I think I'll get back to your question, Haitham, when I'm going to mention the regression diagnostics. So my short answer is no, but it is helpful. What does the intercept in the males females SBP mean? I mean, there were like two groups, males females, and intercept measure using both. Yeah. Okay, so I think I can go back to that. Islam, linear correlation request both X and Y. No, no, but no. No. I know, like even in textbook, they say it's normally it's 2. No. Okay, so I'm going to talk later about this normality assumption. It does not have to be. I can kind of, and I did for my students, I kind of generate non-normally distributed variables. And I look at the linear relationship, and then I get the residuals, and the residuals are normally distributed. So it's all about the residuals. It's not about the variable themselves. As I said, normality assumption helps, but it's just not about the variables. It's about the residuals. So I'm going to get back to that later. Okay, so for the intercept about the sex variable, okay. Here's my, yeah. So this is my output. Okay, so this is my output, and I think outputs are very similar, whatever the software you're using. So you always like have 2 rows, one for the intercept and one for sex. It's not really for sex, it's one for one of the categories of sex. So sex has 2 categories, 0 for males and 1 for females. And all the softwares basically are not systematically going to show you in the output the 2 levels. They are only going to show you 1 level. So what R is showing here, sex.f1, 1 is for females. So it's going to show an estimate for females, but it's as compared to males. Okay, so this is how we read the output. So the output shows the slope or the difference for the group that is shown as compared to the one that is not shown. There is always one that is not shown in the output, which is the reference. So you get no estimate for the reference because you are interested in differences between those levels, okay? So you have to have a reference group. So you don't get any estimation for that reference group. However, you get an estimation of how different the other group is as compared to the first one. So you only get a slope for females, which means a difference for females as compared to what? As compared to the reference group. And this 4 millimeter of mercury here, I'm just like rounding the number, is like the difference between males and females. So which means that the females will have -4 millimeter of mercury blood pressure as compared to males. Okay, so males is not shown just because it's used as a reference group. So now the intercept, it will always be the mean in the reference group. So the intercept that is shown here is the mean in the reference group. And in order to show you that, I have calculated the means here. This is like unrelated to linear regression. I just like tabulated the means in males and females. And the 126 millimeter of mercury happens to be the mean in the males, in the 0 coded people. Okay, so the equation of the line, when actually you deal with binary exposure, is very comprehensive. It has one estimate for the difference between the group that is shown and the group that is not shown. And it has one estimate of the mean in the group that is not shown. So it's kind of a balance. It shows you 2 things because you basically need 2 things. You need a difference between the 2 groups and you need the mean in the reference groups if that's something that is interesting in your analysis. Mainly what you'll be interested in is actually the slope, the difference between the group that is shown and the group that is not shown. So it's really a very good question here just because the interpretation of linear regression model is different according to whether you're dealing with continuous exposure or independent variable like age, or a binary exposure like sex or treatment group. So I think you probably just need to understand how to interpret linear regression output in the case of a continuous exposure and how to interpret it in the case of a binary exposure. It's just like something you probably with practice, you probably get very familiar with. So just like to summarize, the slope for a continuous exposure is for 1 unit increase in age, I will have 1 millimeter of mercury increase in SPP. So for continuous exposure, it's for 1 unit increase in something. For binary exposure, it's actually in comparison between the group that is shown and the group that is not shown. So it's slightly different between the 2. However, I think it's only like 2 scenarios of whether you're using one or the other. So I hope that makes things clear for you, Haitham. Okay, so I think we can carry on. Okay. So now we have compared means between two groups. So I want to extend that and compare means across more than two groups. Okay, like the example that I'm showing here is looking at differences in SBP by BMI groups. So my assumption is, what if people have different SBP values just because they belong to different BMI groups? And I want to investigate that using linear regression. Okay, so I'm looking at the plots here. This is showing like the distribution in each of the groups. And as you can see, so I categorize them according to the WHO categories, I think. Anyway, so the lowest group is actually the underweight people. I don't have that many in my data set. That's why you don't see a lot of points. This is my normal range, and this is like overweight, and this is obese. So like I have like a different distribution amongst the groups. Okay, and I want to see whether can I assume that SBP values on average are different across these groups or not. And the same question as before, do you think these are similar or not? And I think you probably need to look into that, the small differences that are between the groups. And I'm going to use a linear regression model in order to answer that question. So this is my linear regression model comparing SBP to BMI group. And I'm using here BMI group, the normal range as the reference group. As I said for sex, you always need to have a reference group because all your interpretation is around the reference group in the case of categorical variable all the time. So in my BMI example, my reference group is like the normal range. I want to see whether there's an increased SBP, blood pressure for people who are overweight, or if there is any decrease in SBP for people who are underweight. So that's my main question. Okay, so this is my output from R. So I'm going to look at those estimates as I did for sex. So my intercept, I have one question in the chat. Okay, so for the intercept, as I said before, it's actually the mean SBP in the group that is not shown. And the group that is not shown here is group number 2. So group number 1 is underweight, group number 3 are the overweight, group number 4 are the obese. So the group number 2 that is not shown is the normal range. Okay, so the intercept is going always to be the average SBP in the normal range, right? In this example. So now, what about the rest of the values? Yeah, so this is just like a proof. Here calculating the mean across the groups, and it happens to be exactly what was shown in the linear regression model, which means that the mean in the average group is about 130, which is like the same that was shown in the linear regression. Okay, so now what about the rest of the parameters? How can I interpret them? So I'm going to say all the time when I'm dealing with categorical variable, that's the mean difference for the group that is shown as compared to the group that is not shown. So if I look at the, for example, group number 4 here, the 3.7, say I'm rounding, the 3.7 millimeter of mercury is the difference in blood pressure between group 4 and the reference group. The reference group is the normal range people. Okay, so there's 4 millimeter of mercury difference between the top group and the reference group. This is how I always interpret my output when I have categorical variable. It's always like a difference between one group and the other. Right. Okay, so now my ANOVA thing. What about the ANOVA thing? Okay, so I have skipped this line 19 in all my previous output just because like this is a point about ANOVA. So I was like seeing F test statistic. What does that mean? Okay, so this is an example, an important one, by the way. Okay, so my hypothesis is people do have different SBP just because they belong to different BMI groups, okay? So Y bar is the mean SBP value. So I have 4 BMI groups here, and I have 4 means in each of the group. So in each of the group, you have a mean SBP value, and you have an overall mean in the population, okay? So you put people in different groups that will all have in their groups different means, and you want to compare that to the mean overall, okay? So the people here are like the stars that I'm putting in the groups. So like there's 3 people here, there's 5 people here, there's 7 here, and there's 5 here, Okay, so these lines, the blue ones, are the difference between the mean in the group and the overall mean. Okay, so the mean in group one and the overall mean have a difference that is actually equal to that blue distance. Okay, so these red lines are actually the difference between the mean in the group and the individual values. Okay, so these three people have their SBP values, and actually they have some sort of difference between their values and the mean in that group. I might belong to a BMI group, actually. I don't have exactly the same SBP value all the people in my group. However, I have some sort of difference between my individual value and the mean in that group. And the idea is, if we make that assumption valid, that actually people have different SBP just because they do belong to different groups, I'm always going to estimate the mean SBP values by the mean in that group. Because these are my hypothesis. I'm going to use the grouping in order to explain differences in SBP. So what do you think these red bars are? Can you put in the chat how we call these red bars? The difference between the observed value and the mean in the group. Do you have any ideas? How do we call the red bars? Yes and no. Actually, standard deviation is not based on only one bar. Standard deviation is actually based on all the bars. But I agree with you guys. Actually, all the bars are actually a description of the variability in the group, which means that actually it's a description of the variance in that group. So I think I agree with your idea about standard deviation variance. But let's concentrate on only one bar. How can we call that single bar? Your standard deviation or variance is like the collection of the bars. I kind of describe them as a whole in order to get me one value about the variance or the variability in that group. I'm only talking about one bar. How can we call that red bar? Say this is my blood pressure value and this is the mean in my group, okay? So what the red, same standard deviation, standard error is actually same as the variance, is something to describe the heterogeneity in that group. So I'm not talking about like the whole bars, I'm talking about one unit, one single red bar. The whole thing is a description of the variance, standard error. I agree with all that thing. It's a description of the variability. That's a very good point. One single bar means something. The difference between the observed value and the mean value, the value that I'm using to estimate, it has a name. Yes, thank you. Yes, Majdeline, thank you. Residuals, of course. I mean, you had like the idea of variability, which is great, standard error, variance, all that is based on the residuals. We sum those residuals, we square them and get the variance or the standard error when we divide by the sample size. Absolutely. One red bar is a residual. That's the difference between the blood pressure of that person and the value that I use to estimate in that group. Great. Okay, so now I want you to compare two different scenarios. So you see how here 4 distinct groups. So what about this? Okay, so what's the difference between, please in the chat, put some comments in the chat about what's the difference between the first plot here and the second plot? What makes this plot like having some sort of overlapping between the group? And what makes this plot nice and neat and with 4 distinct groups? What do you think the difference is between this plot and the other plot? Please put some comments on the chat. Second plot, SPP reading more closer. Perfect. Getting closer. Some individual BMI is borderline. All those things are valid. Yes. Thanks, Mariam. Thanks, Magdalene. Absolutely. It's all about like things getting closer to the overall mean. So, I mean, in this second plot, I mean, you can see that those blue distances are actually shorter, which means that actually the mean that I'm using to estimate in each of the group is getting closer to the overall mean. That's not a good thing. It means that actually my grouping is not that great just because I end up having a mean that is very similar to the overall mean. So why do I have to group people in different things? And the other thing is, so maybe I can have More standard error, absolutely. High residuals make less differences between the groups. Perfect, perfect. I'm really happy with your answer. I know it's a long lecture, but when I see the answer, I think like you get the main point. Absolutely. More residuals, like those red things, the more you have variability, it's not a good thing. Here, sorry, this is another stuff. Okay, thanks guys, great. Yeah, so the red bars are actually the residuals. When I get those residuals very large, which means that actually people are very different from each other inside of the same group, and you end up having someone here that you don't know how to classify either in this group or in the other. When the residuals get really, really wide, it's not a good thing as compared to these blue distances that get actually shorter. Okay, so I'm going to put a name on, sorry, on this. So the red bars, the residuals, actually describe the within group variability. So how much variability I have inside of my group, how distant are my observation from the mean that I'm using to estimate the SPP in that group. I want those distances to be very small. It means that I'm getting a very homogeneous group. That's great in stats. Okay, so if they get wild, that's not a good thing. It means that I'm getting a very heterogeneous group just because these observations are really different from each other. So it's not a very good classification. Now, the other thing is, so we talked about like within group variability. The blue bars mean between group variability. I want the blue bars to be as large as possible, which means that those groups are very distinct. If I get them really distinct, it means that all those means are different from the true, like the population mean, which means actually it's much more useful to estimate people in the same group using a mean in that group rather than using the overall mean. I get much more information if I use the group means than the overall means because it's very obvious that I have distinct groups. However, when my blue bars get very small, just because the residuals are exerting a lot of pressure, like by their variability, that's something that I don't want to get. So ANOVA is going to really give you an answer about whether it's useful to put people in categories or whether it's not useful, whether there's an association between BMI groups and SPP or whether there is not. So basically, the idea is to compare what we call between group variability and within group variability. And we want the between group variability to win as compared to the within group variability, which means that in my plots, I want this red bars to be small. So now, in order to have this battle fair, I need to have some kind of fair kind of comparison. As you can see, I have so many red bars and very few blue bars, which means that I have as many red bars as the people that I have in my sample and as many blue bars as the number of the groups. This doesn't make the comparison right. So yeah, I have variability coming from the grouping and variability that is coming from the residuals. And I need to make that comparison. So the idea is I'm going to some kind of standardize the amount of information according to the sources of information, which means that the between group variability, I'm getting that information from 4 bars, right? Okay. The within group variability, I'm getting that from the red bars. So what I'm going to do in order to make the comparison fair, I'm going to divide the information that I'm getting from the grouping by the number of bars and the information that I'm getting from the residuals by the number of residuals. Okay, so this is called degrees of freedom. Degrees of freedom are like independent sources of information. How many information do you have? The number of degrees of freedom here is kind of, for example, okay, so let's talk a little bit about that because I think it's important, although I'm running late. So this is like the first group, okay? So all these bars are degrees of freedom. These are sources of information that I want to use in order to describe my line, okay? So now I have 3 red bars. These are three degrees of freedom, 3 sources of information. However, I don't need the 3 ones. I absolutely don't need the 3 ones. Why is that? Absolutely, -1. Why -1? That's okay. So I think you've seen this before, maybe. Okay, thanks, Bara. Okay, Uday, the same. Yeah, so why is that? Actually, I don't need the 3 bars. If you tell me in your class, say we have like 37 people in this class, if you tell me what's the mean, the average score in stats, say, in the class, okay, and then you give me all the scores, individual score, all of you, you don't need to give me the 37 score. You just need to give me the 36 because I'll be able to guess the 37 one. In this example, if you give me the 2 SBP values for these 2 people here on the top, and you give me the mean inside of that group, okay, I don't need to know the third one. I'll be able to guess it. It's really very easy calculation, okay? So instead, it's very important, actually, it's like more efficient to have independent sources of information. If I don't need the 3, I'm not getting the 3. Same for programming, same for data science, same for everything. If I don't need the 3 bars, I don't need 3 bars, I'm going to use only 2. That's because if you give me the mean inside of that group, and if you give me the SBP value of only 2 out of the 3, I'll be able to guess the 3. That's a very easy calculation. Okay. So independent degrees of freedom, that's why I remove, I have to subtract 1. I have 1 comment on the chat. Yeah, I mean, just because it's okay, so this is like the one of the tables I always like see in textbooks. So I think I kind of describe really in a general way the idea about like the ANOVA criteria, which is comparing the variability between the groups to the variability within the groups. And I'm subtracting that by the independent sources of information or degrees of freedom. So I'm getting some kind of ratio. So what do you think that ratio should be? What's the reference value for that ratio? If I have to divide, okay, don't worry about this table. I mean, it's only for you guys if you want to look at it. So let's go back to this. Okay, so ANOVA is comparing the between group variability to the within group variability. Okay, so how much bigger between group variability should I have in order, as compared to the within group variability, in order to say that actually my grouping is associated with the SBP? So how much difference do you think I should have between the between group variability and the within group variability? Is that a reference value that you know? So if I take the between group variability divided by the within group variability, what's the ratio I should be comparing to? In the chat. I think you have seen some kind of reference values for some of the measures of effect with Luai, probably. Because I need to make a decision. So is it good to have like 2 or 3 or 4? What's the number I should be having for a reference? What's the number you think ANOVA is going to use as a reference in order to say that actually the between group variability is much higher than the within group variability, and then that means that actually BMI groups are very useful? What do you think that number should be? So actually I have made the comparison fair by dividing by degrees of freedom. So I should be able to compare 1 to 1. Yes, I'm going to get a p-value, but actually the same for the t-test. I was able to see whether the p-value is going to be significant just by looking at the t-value, actually. So I think I need to have that value as bigger as possible, simply. If it's like above 1, it means that the between group variability is higher than the within group variability. It's like a ratio. So if it's bigger than 1, it's good. If it's less than 1, it's not good. Exactly. Thanks, Luma. It's the same as like the relative risk and all other things, or other like measures of association that are like based on ratios, like the reference value will be like around 1. Okay, so that's my idea. So I'm going straight to the interpretation. So here's my ANOVA in R. ANOVA is giving me like a description of like the degrees of freedom. We mentioned that before, but I mean, I think the key thing is just like to look at the F value here. The F test is the test that is associated with the ANOVA tables. Okay, it's called F test because the test statistic follows like efficient distribution, whatever. You don't need to go into the details. The main important thing, as you mentioned in the chat, you look at the p-value. If the p-value is significant, it means that actually BMI group are useful, which means that actually there's an association between SBP and BMI groups, which means that actually the groups are different. I don't know who are the groups that are different, but I'm sure that the groups are different. It could be one of the groups that is different from the other. It could be all the groups that are different from the other. This is not probably my question. My question is whether there's any difference or not. And the ANOVA table is going to tell you that, thanks to the p-value. Okay, so the F-test associated with the ANOVA table is going to test whether all the groups are equal or not. If the p-value is significant, it's going to tell you that actually not all the group means are equal, which means like BMI is associated with SBP. However, if you want to really know what are the groups that are different from each other, you need to do what we call pairwise comparison, which means that actually you are going to compare the groups 2 by 2. I'm not going to go into that here. It's quite complicated actually, because the more tests you do, the more like errors you might get. So I'm just like putting this here as a hint, but my interest is to look at the overall association for the moment. Okay, so very quickly, just because we run out of time, I mean, I think I have 5 minutes for this. Regression diagnostics is very important. So I'm going to talk a little bit about the assumptions here. So what we have been doing from this beginning is actually to use our sample to make some kind of inference or some kind of conclusion about the population. So there are like few things really that could affect that conclusion. So you really need to know that actually your results are as valid as the assumption are. So you might have like papers with very nice results, but actually the method is really dubious. You need to understand that each test, t-test, even the non-parametric one will have like assumptions. So all the tests will have assumptions, and you need to check those assumptions in order to trust the results. That's really key thing in stats. Okay, so there are things that actually could like bias your estimate, that could bias your standard errors, that could bias the p-value as well. It means that all the group means are different, or at least 2. No, it means like at least 1 is different. But it means at least 1 is different, because the null hypothesis is all group means are equal. If I reject that null hypothesis, my conclusion is there's at least 1 difference. I don't know how many, but at least 1. That's my answer. Okay, so let's go into some assumptions. I have made a short list here because I cannot go into all the details about the assumption, but linear regression. What's really important for you guys to remember is the effect of having outliers. You have mentioned cleaning the data. That's a very good point. You need also to make assumption about linearity. You need to look at the scatter plot before. As we did for Pearson, you just cannot use linear regression if the association is not linear. It just doesn't make sense. The 2 other assumptions, I don't know how much familiar you are with these 2, normality of the residuals and homoscedasticity. So I'm going into that in a minute. So as I said, look at the data first. You don't run linear regression when actually the association is not linear. Otherwise, the software is always going to give you a line. Whether that line is meaningful or not depends on the data. Okay, residuals. The residuals are very, very, very useful. So I think, okay, so I'm going to look at the residuals here. I have put like the R codes in order to extract the residuals after running your linear regression model in R. In Stata is the resid command as well. Actually, in all the software, you always like have a command to extract the residuals. These are the differences between Shukran. Okay, so there is like always like a command to extract the residuals. What we want these residuals to be normal. We are very happy when the residuals are normal. We are not happy when they are skewed like this. Okay, that's the first assumption. Please don't do a linear normality test. It's not about tests. It's about like the shape, overall shape. If you run a test on normality, you always like, the tests are very conservative. They're going to reject normality all the time. This is not what we want. The linear regression model is robust to like small deviation from normality. So it's all about like the shape. Just look at the shape. You don't need any tests here. The histogram looks fine. That's perfect. You can use a QQ plot as well. Okay, so now I'm going to look at the residual plot. So I think I can go here. So this is a residual plot. This is something you can get easily from the software. So this is showing the values that you have estimated, and this is showing the residuals. What we want is to have like a big dot of points. The residuals are normally distributed. You would expect them to be between 2 and -2 for normally distributed data. And you can see here some kind of skew, outliers. And this is because you have some outliers in your data. Okay, so the inspection of the residuals is very helpful in order to kind of see any patterns in the data. So this looks okay. You might accept some kind of deviation. It's fine. It's not a big deal. However, what is a big deal is when you end up having these kind of shape for the residual plots, and that actually means that actually you did something probably not right. Residuals are actually, if you want to have some kind of really very general description of the residuals, is actually what is left over in the modeling. Okay, if you look at the association between BMI and SPP, you want BMI to explain as much variability as possible in SPP. Okay, that's your aim. If you're not getting that, it means you need to add other variables to explain variability in SPP, like age, sex, etc. What you don't want is to put variability in the residuals, to have some leftover variability that is not explained by your model and that is explained by the residuals. Residuals is like the part that is left over. So you don't want to see any kind of patterns in the residuals. That's very important. You want your model to be great as possible, and great in stat means explaining the most of the variability that you can explain. When you don't do that, you end up seeing some patterns of actually things that are probably not linear, things that actually probably not normal, many things in the residual plot that actually are left over, and this is not a good sign. I'm going to get one question. What does the X line in this chart represent? These are the fitted values or the estimated values. These are the values that actually you estimate using the line. Do you remember for like the daughter's height, you pick one mother's height and then you look, you use the line in order to estimate the daughter's height. So all these estimation are put in the x-axis. This is like the output from the linear regression. These are the predictions, if you like. Okay, so you don't want the residuals to be correlated in any ways to those predictions. It means that actually there's something that is left over. So if your residuals are like this, it means that the errors that you make are independent from the exposure. It means that actually you don't have any kind of weird patterns here. You have only a little bit of skew, but that's fine. Okay, so unfortunately, I'm not going to be able to go into all the details about equal variance. This is like what we call equal variance or homoscedasticity in stats, which means that I don't want to see this. I don't want to see a variability that increases with increasing value. I want the variability to be equal. So this is a case, for example, this is my last example probably. You would get this, for example, if you're looking at the differences in salary, for example. So for example, the more degrees you have, you guys have a lot of degrees already, the more degrees you have, the more options for jobs, and then the more like wide probably the distribution of the salaries. You might end up like maybe in an academic, so as you know probably, like the salaries are not that high, or you end up like working private sector. It's not like encouraging people to go in private, but anyways, if you work in pharma company as a statistician, for example, you end up having like a big salary. So like the more degrees you have, the more options you get. So this is not what we want to model using linear regression, using the simple linear regression. There are so many other models that actually could fit much better this kind of distribution that actually the linear regression model that is assuming equal variance. You make the same errors across the line. So this is not good. This is called heteroscedasticity. Okay, guys, sorry, I'm overrunning by 6 minutes already. So, I mean, I think assumption is really very important. I think you probably need I don't know, like there's a lot of emphasis that we put statistician when we teach stats on the assumption, just because, I mean, we want your results to look great and we want the conclusion from your study to be very good and useful. And for that, you need to make sure that it's actually based on a very solid stats. And for that, you need always to question the assumption when you use your tests or regression models. Okay, So I think we are done, guys, for today. So hopefully by now you probably understand like what it means, what correlation means, how to fit a simple linear regression model, whether you're using continuous exposure or a binary exposure. Hopefully you understand a little bit more ANOVA, and anytime you need to remember that, please remember like the distinct grouping and the overlapping grouping. That's the whole idea about the ANOVA. And hopefully we'll see you guys in next week for logistic regression. So if you have any suggestions for me, please put them in the feedback so I can incorporate them in my next session. I'm happy to take some question from you guys, but I think you probably free to leave if you want to. Okay, I'll say bye to the ones who need to leave now, and I can take one or two questions for the ones that are still in the chat. WHO cutoffs for BMI. So there's no question there for me to put them in categories according to how much information they have. So probably what I can do with like clinically relevant cutoffs is, for example, if I'm seeing that in one of my groups I have like really very small number of people, like the underweight, I can collapse two groups in one, for example. This is what I can do. However, if you're asking a question about like the grouping in general, if I don't have any reference, any clinically meaningful cutoffs, like I have for BMI or SBP, then in that case, I need to think more carefully about how to select those grouping. And that's a whole question on what you want to achieve. So I think my advice is to first go for clinically relevant cutoffs. If not, then equally distinct groups, actually. And it depends on how much data you have. You cannot afford having 7 or 10 groups when actually you have a small data set. So it's probably would go for like things that we call tertiles, quintiles, fifths. Okay, guys, if you have any further comments or questions, please put them in the feedback. And I think we'll make sure to put my email in the feedback as well.